It can attack the fuel rods if they are not adequately protected.
Attack the fuel. Today we're going to be looking at a heavily requested real engineering video, specifically the nuclear-powered Mars Express. That's awesome, no connecting flights. Those of you who don't know me, I'm Tyler Fultz. I'm a nuclear engineer with a little over 10 years of experience in the commercial nuclear power industry, from engineering to operations to emergency response. I don't claim to know everything there is nuclear, but I can certainly share some knowledge. Check this out.
In 1965, a young Caltech graduate student by the name of Gary Flandreau was poring over his notes in Building 180 of the Jet
And those are the exact types of paper that I used when I was in school. Awesome.
Propulsion Laboratory, studying the intricacies of using planets' gravitational fields to slingshot spacecraft into the outer reaches of space with no need for additional propellant. The gravity assist, a method of propulsion that uses the gravity of a gravitational body to literally pull the spacecraft into a new trajectory and velocity. As he examined the possible trajectories, Gary noticed something incredible. In the late 70s, a window would open up where the alignment of the planets would allow for a single satellite to pinball its way between Jupiter, Saturn, Uranus, and Neptune, before eventually being spit out to the outer reaches of our solar system and beyond. With this knowledge, a flurry of activity began within NASA and JPL. A once-in-a-lifetime opportunity had been found that would not come about again for another 175 years. And
literal planetary alignment. I mean, I've heard that often in projects when people talk about all the planets need to align for this, and this is the example they're referring to, apparently. That's cool.
It was imperative that the opportunity was not squandered. Planning began, and in 1977, 2 satellites, Voyager 1 and 2, would launch aboard the 3-staged Titan 3E rocket. Voyager 2 would utilize a gravity assist with Jupiter, Saturn, and Uranus before racing by Neptune, before it eventually exited the solar system, while Voyager 1 completed a more direct path, whipping by Jupiter and Saturn before venturing into deep space, moving away from Earth faster than any other spacecraft. Voyager 1 is now over 22.8 billion kilometers away from Earth.
I always thought gravity assist was really cool, using very little fuel, just a little bit to make sure you line up to your planets right, to get the optimal amount of velocity change. The problem is, like you said, you have to literally wait for the planets to align to get your optimal flight path. And if you're a little bit off, it's kind of hard to go back and do it again. But hey, if you can launch at just the right time, it can definitely save you a lot of expenses, because getting all that rocket fuel up into space isn't exactly cheap.
That's so far away that Voyager 1 is now outside the influence of the sun's constant stream of solar wind, meaning it is now in interstellar space, officially reaching the region in August 2012. We, as a species, have now left our mark in interstellar space after a 35-year-long journey, a ponderously long time in the scale of human life, and that was with the help of multiple gravity assists.
I guess that's right. I never really thought about it like that. That technically we've done some level of interstellar flight. I guess it depends on your definition. We haven't gone from one solar system to another. That would take tens of thousands of years with a spacecraft going about that fast. But that's interesting that we achieved that milestone not that long ago, for what it's worth.
While we can build and deploy these technical marvels to investigate other worlds, sending ourselves into space is another thing entirely. And using gravity assists to visit our closest neighbours makes little sense. To date, the furthest humans have ventured into space is to the dark side.
Yeah, that's probably true. It would only make sense if you're gonna orbit Mars for a bit and then go on to Jupiter or somewhere else in the asteroid belt or something like that.
Side of the moon, a mere 400,000 kilometers away. If our ambitions to create colonies on Mars are to be realized, humans are going to need a spacecraft that are faster and more efficient than the ones we currently have at our disposal. Mars is on average about 64 million kilometers away. The fastest and most efficient method we have to reach Mars using the Hohmann transfer method with launch windows every 26 months takes about 9 months to complete. Faster transfer times are possible, But engineers are stuck in a catch-22. It takes fuel not only to accelerate the spacecraft, but to decelerate it too.
Yes.
There are no disc brakes in space. The more we accelerate, the more we have to decelerate too. In order to carry all that additional propellant, engineers will be forced to sacrifice payload weight, reducing the space available for food, water, and other vital supplies for a crewed mission to Mars.
That's one thing that a lot of people don't realize is you have to decelerate just as much.
We can take some solace in the fact faster transfer times will reduce the supplies needed and will reduce the crew's exposure to the high radiation of space.
So dose in space is kind of a lot. You can get quite a bit of radiation from space. Most common source of radiation is cosmic rays. High energy X-rays, gamma rays that you get from the sun and distant stars as well. On Earth, we're protected by our atmosphere, but in space, you don't have that. So you get quite a bit of dose. So even on the shortest possible path, 6 to 9 months, there are estimates upwards of 600 millisieverts from that voyage alone. And that's not counting special solar events such as coronal mass ejections, solar flares, where individual events could get you upwards of 600 millisieverts in a few minutes. But let's say we have good space weather forecasting and we schedule a mission around that, so that's not a concern. That's possible. The dose limit for an astronaut is 600 millisieverts for NASA. For Russia, European Space Agency, it's actually 1,000, and I'm talking career. After all, the minimum dose where an increased cancer risk is evident is only 100 millisieverts, which is twice the annual dose limit for working in a nuclear power plant. So yeah, these astronauts can get way more dose than anybody I've ever worked with. So manned spaceflight to Mars can get you some dose. And not counting cancer risk, early onset, radiation sickness, nausea, vomiting can start around 1,000 millisieverts or 1 full sievert. And 2 sieverts is a pretty high dose that can be deadly in certain situations. It'll at least take you out of commission for a while. Now, when I say that, I'm talking about acute doses, so doses on the order of minutes to hours, not on the order of months. But still, main concern is going to be the longer-term effects like increased risk of cancer. The radiation sickness would mainly come into play during a high-energy solar flare or coronal mass ejection, something like that. And I'm just talking about the flight. Mars doesn't have much of an atmosphere, so it's not going to protect you much more than space. So in this scenario, I'm assuming drones have already built a habitat module deep underground where the soil will block all the harmful radiation, so you can at least take a break from the radiation dose. So this job, if you want to hear about a job that can get you high radiation dose, that would be an astronaut on a long-term mission to Mars or a long mission in the International Space Station. That's going to get you more dose. Not enough to get radiation poisoning, again, barring if you manage to avoid solar flares, but enough to be concerned about.
But what if we could achieve faster transfer times without sacrificing payload? What if we could achieve faster transfer times with even more payload? Let's first examine current technology to see where things could be improved. The Atlas V rocket that brought Perseverance to Mars utilized chemical combustion to propel itself, a method where a fuel and an oxidizer are combined in a combustion chamber and ignited. The resulting exothermic reaction causes the combustion products to rapidly heat up and expand. The nozzle design then directs the expanding gas in one direction to achieve thrust. Getting the most out of our fuel and oxidizer is the first step to maximizing our thrust per unit weight of fuel. There is a useful quantity engineers use to describe this property of fuels and oxidizers, specific impulse. We described in detail what this value represents.
It makes sense to have a unit like that. It's not a unit I'm familiar with. A close analogy to how much energy you get per unit of fuel in nuclear power would be burnup, which is usually given in the units of megawatt days per metric ton of uranium. And because I work in the US, which doesn't use the metric system too well, it's written in a particularly cursed format, MWD divided by MTU, saying metric ton of uranium rather than just saying ton. And a higher number just means it's using its fuel more efficiently, producing more energy per given mass of fuel. Kind of similar.
In our last video on the X-15, explaining how it represents the total energy we can extract from our propellants per unit weight.
So cool.
In that video, we used this equation where specific impulse is defined by thrust force divided by fuel flow rate. This is an extremely important metric for our Mars transfer vehicle. The higher we can push our specific impulse, the less fuel we need to bring, which frees up space for payload. Or we can bring the same amount of fuel and increase our velocity to reach Mars sooner.
Sooner is better in terms of radiation dose. How you engineer around radiation dose is 3 ways. Time, distance, and shielding. Cutting your time, it's directly proportional to how much you cut your radiation dose. So let's say it's 100 sieverts or 100 millisieverts per month, which is a little high, but the number is easy. If you can cut the trip from 6 months to 4 months, well, that's 200 millisieverts your crew's not going to get in terms of dose. The other thing is distance, which doesn't really matter that much in terms of space. You're more or less the same distance from cosmic rays. You'd have to get into deep intergalactic space in order for that to depreciate significantly. And as far as the sun goes, it's more about your relative position to the inbound solar flare or coronal mass ejection. So that one's kind of outside of your control. And shielding, that's going to add a lot of weight. Shielding from gamma rays and other high energy cosmic rays, you're going to need to add a lot of lead to your spacecraft. So good luck getting this thing into space at all. 8 to 12 inch lead armor plating on your spacecraft. So time is probably the best variable you can control in this situation. So yeah, let's focus on getting there faster.
Or even be able to leave outside that ideal Hohmann transfer window. So how do we improve specific impulse? The technology with the best specific impulse currently is ion propulsion. Take the N-Star ion drive aboard the now retired Dawn spacecraft. This engine used electric power to propel ions and achieve astronomical specific impulses.
Ooh, I've heard of this thing. It's really cool.
The engine releases xenon atoms into an ionization chamber and then bombards them with high-energy electrons. The collisions produce a positive xenon atom and more electrons.
The real nice thing is it uses very little fuel.
These electrons are then collected by a positively charged chamber wall, while the positive xenon atoms migrate towards the chamber exit, which contains 2 grids, a positive grid called the screen grid and a negative grid called the accelerator grid. The high electrical potential between these grids causes the positive ions to accelerate and shoot out of the engine at speeds of up to 40 kilometers per second.
That's cool. Granted, we're dealing with very small things, so it's not giving you as much thrust as the chemical rock. But this thing can keep going for a while, and especially when you're in space, there's not really a whole lot holding you back. So continuous acceleration with something like that can get you some high velocities over time. One other nice thing about it is they're small, so you could put them in clusters or something. You can also do a lot more fine control on retro rockets. So a lot of fine tuning in terms of acceleration would be easier with something like this. Problem is, it uses a fair bit of electrical power, and this thing won't get off the ground. Literally. Use this when you're already in space.
Which is vastly higher than what chemical combustion can provide, which has a typical exhaust velocity of about 3 to 4 kilometers per second.
True, but you're not moving that much at 40 kilometers per second. Force is what matters, not velocity by itself. Particles in a nuclear reactor move faster than the speed of light and water. That's where that blue Cherenkov glow comes from. But the nuclear power plant isn't moving.
This exhaust velocity is paramount to achieving higher specific impulses. If we play around with the specific impulse equation, we can see why. Specific impulse equals the thrust force divided by fuel flow rate.
Force, yes.
Thrust force is equal to the mass flow rate times the velocity, while the fuel flow rate is the weight.
Ignore this bit for now. No one cares about you momentum.
Of the fuel on Earth, and thus this value changes to mass flow rate times acceleration due to gravity. And
we use mass flow rate a fair bit in nuclear power, mainly for the steam going in, leaving the steam generator and heading into the main turbine. So I still remember in the control room using the cursed unit, megapound mass per hour. So they're kind of combining metric and using a metric prefix on an imperial unit converted from weight to mass. Okay.
And as we see, the mass flow rates cancel themselves out, leaving us with only exhaust velocity divided by gravity. So it's rather obvious. To maximize specific impulse, we need to maximize exhaust velocity.
Or minimize gravity. Oh wait, we're not there yet.
Ion propulsion is the best technology we have to do that right now. With 10 times the exhaust velocity, the ion drive can achieve 10 times the specific impulse.
I get what you're saying, but as far as specific impulse, but ultimately you are talking about moving something, so force is still relevant.
That's a phenomenal increase. So why aren't we using this technology for interplanetary missions? Mass flow rate may not be important to specific impulse, but it is massively important to thrust. As we saw just now, thrust force is equal to mass flow rate times the velocity. Chemical combustion happens extremely quickly. It is, after all, a controlled explosion, and so it is capable of accelerating millions upon millions of molecules out in a very short space of time, leading to a high mass flow rate. High thrust is very important for particular maneuvers, like capture burns, where a rocket will fire to slow its speed down enough to be captured by a planet's gravity. The window for this deceleration may only be a few hours, where ion propulsion simply cannot provide enough thrust in a short enough time to successfully complete the maneuver. Ion propulsion simply does not have the mass flow rate necessary to achieve high thrust. It took the Dawn spacecraft 4 days to change its velocity by just 94 kilometers per hour. To increase our ability to
You would need a lot of them, in other words.
change velocity quickly, we need to increase the mass flow rate. To do this, we need to increase our input power. For ion propulsion, that power comes in the form of electricity, which provides the energy to ionize our propellant and accelerate it using an electric or magnetic field.
And that's where the trade-off comes in terms of what you're loading your spacecraft up with. It can be a bunch of chemical fuel or the means to generate this much electricity for your ion drive. And I think this is where he's going to get to talk about nuclear power, because nuclear power produces the most, because nuclear power is so energy dense that it can produce that kind of electricity.
Current generation ion-propelled spacecraft use solar panels to provide that electricity. The Dawn spacecraft has panels capable of producing 10 kilowatts of power when orbiting Earth.
The problem is, when you get further away from the sun, solar becomes less useful. I mean, solar does become more useful if we were going the other direction to, say, Mercury, for some reason. But solar power on Mars is way less effective than solar power on Earth. And solar power on Earth isn't that effective. At least compared to nuclear. Solar does have its places, but I'm biased.
Which diminished to 1.3 kilowatts by the time it reached its destination in the asteroid belt, 3 times further away from the sun. Scaling that solar power becomes impractical very quickly. NASA estimates that a Mars transport vehicle would need at least 400 to 2,000 kilowatts of power to carry astronauts and cargo to and from Mars.
That's a lot of solar panels on Mars.
So, how do we power something like that?
It'd be like, wouldn't that be something? It's like, hey, it's enough solar powers on Earth, but you don't have enough solar panels to get back, and you're stranded there. That's a problem.
Nuclear power is the only thing that can give the power density needed to make this viable.
Oh, yes.
This isn't a new concept. In 1961, the Atomic Energy Commission and NASA launched the Nuclear Engine for Rocket Vehicle Applications program, or NERVA for short. This program developed and ground-tested 20 reactors before it was disbanded in 1973 due to budget constraints, but was recently revitalized when the US Congress approved $125 million in research funding for nuclear propulsion. There are two primary types of nuclear space propulsion: nuclear electric, which would power an ion drive like we saw above, and nuclear thermal, which was the focus of the NERVA program. So
the one on the left is a nuclear power plant in space, and the one on the right is, rather than converting to electricity, we're just going to use the reactor to provide thrust directly with its intense heat.
Let's start there. Nuclear thermal propulsion works by harnessing the heat created during nuclear fission to provide the energy needed to expand and accelerate a propellant through an exhaust nozzle. Here, the nuclear reactors work in much the same way as a nuclear reactor here on Earth would, where a chain reaction of neutrons colliding with uranium atoms splits them and creates more
Is this nuclear popcorn? That's funny, but potentially misleading. I mean, what he said was correct, but the visual just made the neutrons look smaller than they do in the actual atomic nuclei. But maybe you're not supposed to take this bit too seriously.
Neutrons and a tremendous amount of heat. To capture this heat,
yeah, it almost looked like I'm guessing those were supposed to be electrons caused the fission, which obviously not.
A propellant, typically liquid hydrogen, is pumped through the reactor core, which will cool the reactor core and pass the heat to the liquid hydrogen, which
gas-cooled reactors are a thing. They can be quite efficient in terms of cooling.
Rapidly expands and accelerates out of the thruster nozzle at high speeds, typically around 8 kilometers per second, twice as fast as chemical combustion, and thus about twice the specific impulse, at around 887 seconds.
Yeah, that scales.
However, it's not all sunshine and rainbows. Using hydrogen as a propellant comes with some issues.
It's explosive, so you don't want to leak.
It can attack the fuel rods if they are not adequately protected with a material that is resistant to hydrogen's destructive tendencies.
Attack the fuel rods.
Liquid hydrogen also has to be stored at extremely low cryogenic temperatures, and if it is allowed to rise in temperature, it needs to be vented to prevent an explosion. And on top of this, the tiny molecule is so small it can slip through seemingly solid materials, as it can fit between the spaces of larger molecules. This makes it unsuitable for long storage periods, and ideally, we want a Mars transfer vehicle that can...
I mean, there are hazards with storing hydrogen on Earth. It doesn't necessarily change much. The biggest disadvantage I see with this, though, is it's going to add a good bit of weight, because you not just need the nuclear reactor, you do need shielding from the nuclear reactor to prevent the crew from getting dosed. Now, I'm assuming it's going to need its own separate module, its own and containment structure. Because neutron radiation gives way more dose than even the gamma radiation they'd be exposed to in space. Especially for an operating nuclear reactor, you're going to need to design some radiation shielding and some containment structure around that. Not to mention all the redundant safety systems you will need, just like you have on nuclear power plants on the Earth. You can do it. It's just going to make the spacecraft. So the robust design and testing, redundant safety systems, comprehensive safety protocol training for the astronauts, which that part shouldn't be that big of a deal. Astronauts are generally trained on radiation safety on some level. They'll need to be trained on how to operate a nuclear reactor, which, again, for an astronaut should be very doable, but that is just another thing to add on there. Do I think it could be done? Yes. Could it be done safely? Yes. Is it going to be expensive? Yes, just like any new technology.
Sit in orbit around the Earth or Mars for extended periods, waiting for the crew to arrive and begin its journey between the planets. Then, when it arrives, the crew descends in a separate vehicle, leaving the transfer vehicle parked in orbit once again. Liquid hydrogen is just a pain to use in this application, so why use it? Because when it comes to maximizing exhaust velocities and thus specific impulse, low molecular weight exhaust products
Yes.
are important. Assume for a moment that all the heat energy we input into the system is converted to kinetic energy in the exhaust products. Kinetic energy.
It isn't 100%, but this method's going to be way more efficient than that of a typical nuclear power plant because you're eliminating the intermediate steps of, ooh, I have to convert that to electricity. Ooh, I have to convert the electricity to drive something to get back to kinetic energy. So you're eliminating 2 intermediate steps. So you could probably get this one pretty high.
Equals a half times the mass times the velocity squared. To find the velocity, we can rearrange this equation. So now we see that velocity equals the square root of 2 times the energy divided by the mass. It's clear here that increasing the mass of the exhaust particles will decrease the velocity of our exhaust. Hydrogen is the lightest element and thus maximizes specific impulse. If we were to use another propellant, it would be extremely difficult to make a nuclear thermal propelled spacecraft with a high enough specific impulse to justify its use. The next lightest gas is helium, which is twice as heavy as hydrogen, and thus will reduce our specific impulse by the square root of 2, nearly negating all the advantage nuclear thermal propulsion can provide. The next lightest element, which isn't a solid at temperatures we require, is nitrogen, which is 14 times heavier, and thus would decrease our specific impulse by the square root of 14, which is 3.7 times worse, making a nitrogen nuclear thermal engine worse than a traditional combustion engine. So, we can't get away from this hydrogen storage problem, and if we hope to use nuclear thermal propulsion, we are going to need to figure out how to keep hydrogen cryogenically stored for extended periods.
At the nuclear plant, we use hydrogen to cool our main generator. And it has some good advantages in that its thermal conductivity is 10 times better than air. It's low windage, it's light, has a very high specific heat. Oh, and it doesn't conduct electricity. That one's also pretty important. And we keep it at a concentration of well over 98%. So it's too rich to burn. Only risk is you don't want a hydrogen leak. By the way, in radio communications in the plant, you refer to hydrogen as Hotel 2 and nitrogen as November 2, because you don't want to misspeak saying hydrogen and nitrogen because they sound kind of the same when you're on the radio, and you do not want to get those two things mixed up.
If this problem could be solved, the higher specific impulse and higher thrust could cut our transfer times to Mars by half, or potentially open launch windows outside of the ideal Hohmann transfer window.
That is also cool.
So, can we get around this hydrogen storage problem while using nuclear power to achieve?
Well, you can always raise the pressure, though that means you got to build vessels that can withstand that pressure. You can store it in a chemical compound such as ammonia and then separate it, but that also adds complexity. So I see what he means by the problem. You'd have to kind of add complexity to work around that, with which again takes money and takes up valuable space and valuable mass that you're trying to reduce on this trip.
Achieve higher specific impulses. This is where ion propulsion becomes really attractive again. One massive advantage in ion propulsion's favor is its ability to use heavier, inert, and easily storable noble gases as propellants, like xenon or krypton. This goes against our previous understanding where low exhaust molecular masses are beneficial to higher exhaust velocities.
So we're switching to nuclear electric, so that's basically the main disadvantage. The main trade-off there is you're going to have to convert it to electricity to make your ion drive go, which is going to cut your efficiency down to like 25 to 30%, something like that. You can gain higher efficiency than that on Earth in a nuclear power plant, but that's because we have complex moisture separator reheaters and feed water heaters and everything you can to squeeze just that little bit of extra efficiency out of to get you up to 33%, 35%, 40% for the better designs that operate at higher temperatures. But that's not practical on something that moves back and forth in space. This is more of something that's going to stay on for upwards of 18 to 24 months, where that incremental 1/10% efficiency gain can change your bottom line by several $1,000,000.
This is possible because we are using electric power to launch these atoms at tremendous speeds. The ion exhaust velocity is defined by the charge of the ion, the voltage that it is being accelerated by, and the mass of the ion. The charge and mass of the ion are defined by the propellant choice, but we can scale that voltage very high before we hit a limit in performance due to material properties or some other physical limit. For combustion or nuclear thermal engines, we are converting thermal power to kinetic energy. That thermal power is difficult to scale. Chemical combustion is limited by the energy we can liberate from the chemical bonds of the propellants and by the temperature our engine can operate at before it melts. This is a problem for nuclear thermal power too, which has to run extremely high reactor core temperatures of 2,500 degrees Celsius to achieve exhaust velocities high enough to justify its use.
The irony in that statement, so fissioning a uranium-235 atom gives you about 200 million electron volts worth of energy. Now, an electron volt is a tiny unit, but here you're talking about an individual atom. So this is a very microscopic scale. So 200 million electron volts for an individual fission event is a huge number. However, in terms of what it's used to heat and provide thrust through burning hydrogen, and the energy in burning those hydrogen molecules is on the order of tens of electron volts. So it's interesting that
specialized nuclear fuel designs are needed to survive these temperatures, and any higher would destroy the reactor. For reference, this is an order of magnitude higher than nuclear reactors here on Earth need to achieve, which typically operate at about 300 degrees Celsius, as they are in effect just boiling high-pressure water.
He's referring to reactor coolant temperature, not fuel temperature. The reactor coolant temperature average that I'm used to is about 590 degrees Fahrenheit, which figures out to close to 300 Celsius. But the actual fuel centerline temperature of the actual fuel itself, let's see, using Celsius, 1200 to 1500. So we're talking more like double rather than 10 times.
Ion thrusters do not come close to the operating temperatures that thermally driven engines do, and we can crank that voltage up high enough that the added mass of the ion barely matters. We are still achieving 10 times the specific impulse of traditional engines. Could we use a lighter propellant to increase specific impulse? Of course, but the advantages of using propellants like xenon and krypton are so good that the drop in exhaust velocity and specific impulse are...
Another bit of irony is nuclear power plants, at least pressurized water reactors on Earth, they generate xenon. It's a common fission product. In fact, it's known as reactor poison because the production of xenon slows down fission reactions. So it's something reactor operators have to compensate for when they're either raising power or lowering power. Though at steady state, it does reach an equilibrium value, so it's not really a concern unless you're moving the reactor up and down.
Worth it. Being inert, they can easily be stored over the long thrust cycles ion propulsion needs, making them the ideal propellant for long-duration interplanetary missions. Larger atoms like xenon also hold onto the electrons in their electron cloud much looser than smaller atoms like hydrogen. So it takes less energy to ionize xenon than it takes to ionize hydrogen.
That's interesting. I didn't actually realize that. I mean, we're not talking, these numbers are right. We're not talking by a whole lot, but it's enough that it'll make a difference over time.
So this reduces the electrical power needed for the first step in our ion propulsion process. And most critically, higher mass exhaust improves thrust. This equation defines the thrust an ion propulsion engine can generate. Where ion mass forms the denominator of our specific impulse equation, it forms the numerator for our thrust equation, meaning an increase in ion mass will increase our thrust, which is the spec that ion propulsion struggles with most, a worthy trade-off. To use nuclear power to generate electricity in space and power our ion drive, we will need to figure out a way to cool the reactor core. For the nuclear thermal engine, the propellant acts as a coolant. For the nuclear electric engine, we will need a closed-loop coolant system where we do not expend the coolant, but keep it in a cycle between the hot engine and a heat exchanger.
Now that a closed loop, most reactor coolant systems on Earth look like that, include whether you're using water or gas as a coolant. That's what most things look like. So this is looking more and more like a terrestrial nuclear power plant.
The only method we have to dump heat overboard in space is through radiative cooling. So, a nuclear electric propelled spacecraft will need massive radiator fins where this coolant can pass through. This is feasible,
nuclear
but
radiator.
We have a long way to go with developing nuclear engines for space. And even with this added power, nuclear-powered ion propulsion would still be on the low end of thrust. In all likelihood, these ion-propelled engines will need to be a hybrid engine that can use chemical combustion for high-thrust maneuvers, or if the problem of...
Okay, now we're getting into more complicated stuff. If you're using hybrid engines, adding that extra layer of complexity, I wonder, would that actually be less expensive, both in terms of cost, time to get to Mars, and ultimately how much radiation dose your astronauts are getting, than nuclear thermal, even with the hydrogen storage challenge he mentioned, which still I don't see as the biggest challenge for that. But the challenges for this will still be there, because it's a nuclear reactor. You're adding in a coolant loop and an electrical power system. Now, conceivably, this could also power coolant loop and an electrical power system. The reactor is still going to need containment. The reactor is still going to need independent safety systems, multiple of those. So that's effectively a wash between both of those designs. I don't know. I'm not actually sure which one's better.
Term hydrogen storage can be addressed, a nuclear hybrid engine is extremely attractive, where our high thrust burns can be produced by the nuclear thermal engine, and then through neutron absorbing control mechanisms like these rotating drums, where one side is coated in a neutron reflector and the other is coated in a neutron absorber.
So neutron reflector. So neutrons normally cause fissions and then they just keep going. The purpose of a reflector is to keep them in the core for longer. And materials that are good at that are solids, would be something like beryllium or graphite, which is also a good moderator. Generally, things that are good moderators are good reflectors. And by moderator, I mean thing that slows down the neutrons so they can actually stick around and cause fissions. So a reflector changes the neutron's direction, and a moderator changes its speed. In a pressurized water reactor, water actually acts as a good reflector, a good moderator, and a good coolant all in one. But water's pretty heavy to bring into space. Also, there's no gravity in space. And he mentions absorbers, so things like control rods. Boron, for instance, is an absorber, just slows down nuclear reactions.
By simply rotating these drums, the engine temperature could be lowered and switched to a closed-loop coolant system that could power our electric generator and provide extremely high specific impulse and a gradual increase in velocity that could drastically cut our travel times to Mars, or perhaps allow humans to venture even further into our solar system and begin our gradual exploration and settlement of our cosmic neighborhood.
Now, which one do I think is better for Mars specifically? So keep in mind, while I do know nuclear things, I'm not necessarily an expert on space travel and mission parameters. So if any of you work for space programs or happen to be astronauts or something, please feel free to poke a lot of holes in this. I'm thinking nuclear thermal for Mars, because you want higher thrust and shorter transit time. The main concerns seem to be time with that mission. But if you're doing something that's longer, deep space, maybe with a bigger craft, that speed wasn't as much of a concern, and you just wanted the thing to be as efficient as possible, as gradual as possible, maybe with more modules and more systems that you could do to accommodate the full-size nuclear plant and maybe some additional radiation shielding. Maybe nuclear electric would be better suited for that. But that's just my thoughts. Thank you very much for watching. I'll see you next time.